Good evening, you guys who are joining us for the It says there 8:30 a.m. It's actually 4:30 in the afternoon. I must have just hit a different setting, so it's 4:30 in the afternoon. In fact, let's actually go and change that to 4:30, because that's actually absolutely what that should say. So yeah, 4:30 p.m. You can see there. So here we go. Yeah. So if we go into there, we've got live in 6 days, October the 2nd, 4:30 p.m. GMT, and we're going to go through in this session. We're going to go through a series of ideas about the classroom, but particularly we're going to focus on 7 specific methodologies that you can pick up and run with immediately. That's going to increase student activity in your classroom. So they range from questioning techniques to group work activities to little games, things that you can literally just pick up, and you're up and running with those ideas. So I can't emphasize enough. Come along live. It will also be available on review. Come and take part. We'd love to have you there, and it's completely free. So come along. I'll also put a link to that session in the description of this particular session you're taking part in right this moment. The other thing I was going to say to you is that you should all now have access to your teaching biomechanics course on the mypexam.org website, and I'm logged in here as a user. Marta's actually our head of languages, and you can see here I've got a 12-part course which is going to detail all of the studies that we do within this qualification. So if I was to go into lesson 1, for example, we'd be able to go in there and we'd be able to have a look and literally view the 1 hour 40 minutes of session 1. But perhaps more importantly, I could go ahead and think, right, next week we're doing vector drawing, and I can go ahead to the quiz on vector drawing, and I can take some questions, and it's just going to be for me to do a little bit of prep in advance of that session. No one's measuring you, no one's checking what you're scoring. It's just for you to have a bit of practice. You can have a go at answering questions. I'm going to answer a couple here, for example. This one I happened to get right, even though it was a guess because I didn't read the question. And I'm going to go forward. I'm sure I'll probably get this one wrong. And I'm just going to do a couple of questions and see where my knowledge is with things. Okay, so this one, I'm going to go for that one. So it's just a nice way for you to cover a bit of material in advance of the session that we're doing. Okay, we'll always provide you with a note sheet. You've already got the resource pack, and now you've got the opportunity to take some quiz questions. And of course, you can review the session on demand within those locations once they've been broadcast live. And my very last point for you guys, I actually don't have this on the screen, but my very last point for you guys is that you should now all have received your 80-page Biomechanics resource pack. If you haven't seen it in your email, it's probably in your spam folder, so go and retrieve it from that spam folder and get it from there. Obviously, anyone that doesn't think they've received it, just let us know, and we'll get it to you immediately. Okay, so again, I really encourage you to come along to our increasing student activity session. That's on Monday. You can also get involved you can also take that on demand afterwards. Obviously, we'll be back together next Tuesday, and again, have a play with your teaching biomechanics course on the website, and hopefully you should have plenty of fun with it. That's all from me. We'll be starting the session immediately. Okay, we should be live, I hope. We've just had a very good evening all, first of all. We just had a very interesting moment where, just for a moment there, our microphone completely failed on us. So we're actually going to be switching between a couple of different mics tonight because the one I thought I was going to be using isn't actually working, and I'm not sure why yet. Anyway, we're fine. So just be aware, you might get slightly different sound variations when we switch between different scenes in the show. Okay, so look, we're going to get on with it pretty much straight away. So there's going to be no delay here or introduction. We're going to get straight in. We're initially going to review what we did in session 1 on Newton's laws, quickly go over that with a couple of the resources, and then we're going to move on to look at force, motion, and centre of mass. And if we squeeze all that in, we'll look at some past paper questions at the end. Otherwise, we'll include those at the start of next week's session. A couple of just practical things from me. I hope you've got access now to the online course, the on-demand course. We'll always post the materials there after the sessions have taken place, but also you should have access now to the 80-page resource pack. That's been sent out to you. If you haven't opened it or seen it in your inbox, check your spam. If it's not in there, then get in touch and we'll resend it out to you, but hopefully you've all got that there. So without further ado, we're going to go straight into the session where we're going to look at force, motion, and centre of mass, and initially we're going to have a look at Newton's laws again. Ready, Marta? Okay, let's move on. Okay, so here we go. Let's get on with this. So look, we know where we are. We're session 2. We're teaching force and motion. If you didn't sort of listened to me talk about this classroom model in the session last week, I urge you to go and have a look at the part of the broadcast last week when we talked about the classroom model. I just wanted a couple of very quick reminders, really. What we're arguing for this optimal model for really any classroom, but let's put it in the terms of biomechanics right now, is that what we're talking about is this self-paced learning environment, And what that means is that all of the learning is completely owned by the students. They can effectively move through resources, through activities, through tasks, through experiences at a pace and a rhythm which suits the individual learner rather than be taken through as a class. But of course, within a very, 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 very rigorous environment where checking and ensuring is an absolute dominant feature. So just to remind you, we've got zone 1 of our classroom, which we call terminals. In the terminals area, students with us, they take short online tutorials and quick quizzes. At least they do for now. More things on that coming soon. And students effectively self-pace their way through the core teaching. The second area over here is what we call the quiet study. Okay, quiet study. And quiet study is really where students go for any paper-based experience, whether it be questions, whether it be worksheets, whether it be textbook research, whether it be answering a past paper, whatever. They do that there, and those resources are available proximally to that environment. The third area is over here. We currently call that the play space, although we are going to rename it. And here students go to manipulate things with their hands. We're going to have a little look at some of those examples today, actually. And that's all about developing a sense of intuition for the key understanding. As is the quiet study area, actually. It's all about developing an intuition. And that intuition means, broadly, that really, regardless of what question type or what challenge the student's going to get in terms of a question, they're going to be able to have a really good answer, go at it, because they've built their understanding on a concept of intuition. Okay, a deep grasping of the conceptual aspects of what they're trying to learn. And finally, we have this area here, which I'll write over here. This is what we call small group teaching. So if we have evidence that student A and student F are struggling on topic 7, the teacher would specifically intervene with those two students, going over some material, coaching, supporting them, reassuring them, whatever is required. So that's the classroom that we work in. And of course, the resource pack, which we've sent round to you, again, just to repeat, if you haven't received that in your email, it's almost certainly in your spam folder. So have a little look in there if you haven't opened that and got access to that yet. It's designed for this classroom. So, we've got note sheets for taking tutorials. We've got worksheets and past paper questions to go in the quiet study area. We've got activity sheets to go here. And of course, you guys are going to manage the small group teaching areas. All right, let's get on with it. Quick recap of Newton's laws, first of all. We went through Newton's 3 laws in our first session, and effectively what we did there... Folks, just bear with me 1 second, please. Oh, apologies. I have this cough I just can't get rid of. It's a little bit annoying. So anyway, let's get on with it. We looked initially last week at Newton's first law, obviously. So we've got law 1 up here, the law of inertia, okay? And I'm not going to go through all of these examples, and I would encourage you to do exactly that. But what I'm going to do is I'm going to highlight one of these examples and show how we put some kind of application, some language around this. I'm going to consider the first one as done because we covered it effectively in the past paper question we did in session 1. So what I'm going to do is I'm going to have a look at this example here of the cyclist at maximum speed. So look, you want to encourage your students here to go into a prose-based answer. Okay, so you want a prose-based answer because that's ultimately what the student's going to do. So I'm going to do almost the opposite and kind of bullet point this for speed, but obviously you're looking for the student to write this into prose. So a couple of points that I would be looking for in this response. We have got in this example, probably writing too big here to fill all this in, we've got maximum speed. So by definition, we've got no, I'm going to put acceleration for A for acceleration, and we've got no D, we've got no deceleration. They're at maximum speed, which means that it's a constant velocity setting, no acceleration, no deceleration. So how would we refer to that? We would say zero net force. Okay, so remembering what we looked at last week, we're saying that there is a zero net force. Remember, net means total. There's a zero net force acting in that environment. And we'd go further and we'd say, we actually say that the net forces which are zero are what we call the external forces. the external forces. And we know from Newton's first law, a body will continue in a state of constant velocity unless compelled to change its state by external forces. Well, the external forces here are zero total force, so it's not going to change its state of motion. Okay, so we go further to say that this applies to both vertical, and you could go into detail here, and horizontal forces. So we could go into detail and we could say, right, on the vertical side, we have got the weight force is being cancelled out by the ground reaction force, therefore zero net vertical force. And in terms of the horizontal forces, we have got the air resistance being cancelled out by the friction. We have got zero net horizontal force, therefore we have total zero net force acting on the body, and we have no acceleration or deceleration, we have constant velocity. So that is the thought process you're looking to encourage in your students. Now, will they be able to get that first go? Will they be able to put the language around that first go? No, they're probably going to need a couple of attempts. They're probably going to need to refine their answer. Even more reason, as we said before, for what we would describe as self-paced learning. Because self-paced learning, one of the objectives of self-paced learning is mastery in every topic. So be clear, if your students write some kind of dodgy answer to this response, first of all, and they never come back to it, it could be because they're a lazy little blighter. Okay, it's possible, but it's far, far, far more likely to be the case that they've moved on. They're in a class-paced environment and they don't have the opportunity to come back and to master that, go through the resource and experiences they need and then master that. Anyway, I'm going to move on for that. Obviously, when we come to these other examples, whether it be, this one's a good one here, accelerating out of the blocks, we're going to be sort of saying something different here, aren't we? We're going to be saying that there is acceleration. Okay, so we're going to say that there is acceleration. We're going to be saying that there is a net force forward. We are going to be saying that they've overcome inertia. Overcome inertia. My handwriting's terrible tonight. And we are going to be saying also, I mean, we'd almost go into sort of Newton's second law by saying that the force applied to the blocks has to be sufficient to overcome that inertia. So the external force has to be big enough to get them out of that block. If they don't push hard enough, they're not coming out of there, right? And they're certainly not coming out of there fast. Newton's second law, we looked at as well, the law of acceleration in last week's session. Basically what we're saying there is that acceleration is proportionate to the force acting and in the direction of that force. And we've got this equation of F equals ma. Okay, so we've got this F equals ma, and it's a really important equation for your students to know. And what we're saying here for the intuition is that, and you see it here, if the student covers up the F, that means that they can calculate the F by multiplying the mass times the acceleration. Likewise, if they cover up the A, they can calculate A by force over mass, and so on. Now, for many of you, you're going to be in a situation where you know, on your courses, you don't need to put numbers into this for kind of exam purposes, but put them in anyway for intuition purposes. So what we've got here, identify the equation for working out mass. Well, what do I do there? In fact, I wonder if I can actually get rid of my little squiggle a minute ago. What do I do there? There's my squiggle. So I've got to work out this time mass. Well, I'm going to cover up mass. And okay, for mass, I've got force over acceleration. Force, let me just put it like this, divided by acceleration. Okay, so that's how I'm going to calculate mass. Identify the equation for working acceleration. Well, I know it's force, and this time I'll put it in this format, divided by mass. Okay, so we can use our intuition to understand the relationship between these variables. And the other thing I just repeat what we said last week is that broadly speaking, mass does not change in the sporting environment. Sorry, and therefore, generally force and acceleration are proportionate to one another. Okay, your choice obviously on this one, whether you encourage your students to actually put numbers into this. We've got a situation here, golfer swings her club at 50 meters per second squared. To strike a ball weighing 0.05 kilograms, how much force did the golfer apply? Okay, so what we've got here is that we can calculate force. We know that force equals mass times acceleration. Force equals ma. So we're interested in the force, and now we can take the mass, and we can take 0.05, and we can multiply that by the average acceleration. Okay. and that is 50 meters per second squared. And we can multiply that. And if you've got a calculator, feel free to calculate that. But that is 2.5 newtons. Okay, 2.5 newtons. Okay, so we've got this 2.5 newtons, which is the force applied in this environment. We can do another one, I suppose. Let's do the volleyball one. A volleyball player spikes the ball. She strikes the ball with a force of 5 newtons. The ball weighs 0.3 kilos. At what velocity will the ball travel? Well, okay, what we've got to do here, we've got to take acceleration equals force. Wow. Whoops. Sorry, folks. Equals. What am I doing? Equals force. Acceleration equals force divided by mass. So therefore we can get acceleration now by taking the force, which we've got over here is 5, and we can divide that by 0.3. And again, feel free to calculate this yourselves, but that's going to give you a result rounded to single decimal place of 16.7, and we must put our units in meters per second squared, ms to the minus 2 meters per second squared. And obviously you can go and do the third one as well, but the point we're trying to get to here is, okay, whether your particular course includes equations or not, or includes calculations or not, those calculations can get to the heart of the concept. It's your call, obviously. And finally, as a quick review, and I'm only going to bullet point this, we've got an interesting situation here, and when your students do this one, they may ask you very difficult questions, and let me explain why, because there's an intuition around this one that it's not as obvious as it might first seem. A rock in space has a mass of 10,000 kilograms. It has thrusters which can generate a force of 500 newtons. I mean, very likely, probably way more. Imagine the rocket was in space, stationary, and then it turned on its thrusters. Prove that you understand Newton's laws by explaining in detail what would happen and identify the acceleration. So for me, I'm going to go through the explanation. The calculation is broadly exactly what we've just done. So the key thing for me is that we're going to make some key points. Let me do that again. We're going to say that thrusters generate force. So it's important for me that I acknowledge that these thrusters are generating a force. Okay, so that's my first point. But this is kind of where it gets interesting for your students, because they're going to say to you, yeah, but they're not pushing against anything. They're in space. There's not anything to push against. Newton's third law, equal and opposite reaction. And broadly, they'd be right. And I'll come back to that very point in a few moments' time. Now, a couple of things. We're going to carry on with our theory. Acceleration. We're going to say acceleration is going to be proportionate to force acting. Okay, so acceleration is going to be proportionate to force. So we could say more thrust, more force, more acceleration. Okay, so that's perfectly legitimate to say. But we're also going to say more thrust, more force, more acceleration. But we're also going to say that in this case, the mass goes down slightly. So by releasing the fuel, the mass of the overall body, the rocket as a whole, reduces. So in this equation, you even get greater acceleration because the mass itself is reducing and there's less resistance, or there's less inertia once that fuel has been released. So so we could say therefore there is slightly less resistance. There is slightly less resistance. Okay, and of course what that means is we're going to get a greater acceleration, a slightly less resistance. And that resistance, by the way, we're talking about air resistance and gravity. And then we'd say, okay, therefore, let me put my bullet point in there, therefore, therefore we get acceleration forwards, because we want to mention the direction as well. We could say northwesterly, we could say to the left. Okay, therefore acceleration forwards. Now this is the key point I'd get to on this one. Obviously you want your students to calculate as well, but this is the key point I get to. Your students are going to say to you, right, when those thrusters act backwards, there's nothing for them to act backwards on, unlike the Earth when we push off the ground, say, and we accelerate forwards. Now, in space, it is different because, of course, you've got less to push off. But, of course, in terms of the forward action, you've got less air and gravitational pull to stop you moving forwards. So this proportionate relationship effectively remains constant, because we've got less resultant force or less reaction force, but we've also got less resistant force as the rocket begins to move forward. So the student may well raise that with you, but the intuition we're looking to get to is that, of course, when we're on Earth and we're jumping up into the air, for example, yes, we can push off a solid object, which is the Earth, and that, of course, allows us to get greater reaction forces, ground reaction forces. But of course, on Earth, we're also battling against air resistance and the pull of gravity, unlike in space. Okay, you're pushing against less, but there's less to prevent you going forward also. So therefore, you effectively get the same proportionate relationship. So again, there's some really interesting experiences for your students to go there. I can't emphasize enough that they could go through those worksheets. Really, the objective is that they get stuck plenty. And of course, what you're looking for them to do is you're looking to solve those problems, or use intuition to solve those problems, and then to write coherently. Secondly, they need past paper questions. They need mark schemes. They need to be going through those experiences, because all this intuition needs to be placed into that context. And if you go back to the questions that we did last session, it will cover some of that detail really well. I'm just going to pause just for 1 second, folks. Okay, good. We're in good shape here. We're making progress. So look, let's move on to force and motion, and we're going to do quite a bit of work here on centre of mass and stability as well. These things do overlap with each other, by the way, as they do with Newton's laws. So you should see that theming and trending through the topic. So look, let's define force. We've mentioned it on numerous occasions so far. Let's define force first of all. A push or a pull that tends to cause a change of motion. Okay, so if you now put that into the context of Newton's laws, a push or a pull, we can talk about that being an external force that tends to change the state of motion. Change of motion. Well, we could also write that as overcoming inertia. Overcoming inertia. Okay, so one of the words I want to sort of draw out with you in terms of this definition is this one here: tends. What do we mean by that? Well, look around your environment now. Spot something light. Around me, I've got pencils, I've got some paper, I've got my mobile phone, which is on silent, non-vibrate right next to me. Why don't I turn it off? I don't know. But anyway, I can apply a force to those objects, and I can move those objects, or I can change their motion. So my phone is currently sitting in a state of constant velocity, stationary, and I can apply a force to it. I don't know if you heard that, and it moves. Okay, so I change its motion. However, there's other things around me that are really heavy. I have a desk. If I apply the same force to the desk does not change its motion. Okay, it changes the forces that are being applied to it, but its motion doesn't change, because there's only a tendency. In other words, the push or the pull has to be of a sufficient force to overcome that inertia. And of course, the greater the inertia, the greater the push or pull needs to be. So if you start applying that to a really heavy weightlifting bar, for example, of course, it's got one heck of a lot of inertia if it's very, very heavy, and we've got to apply a much greater force to overcome its motion. Okay, so that's important to understand the relationship between force and motion. Forces do change states of motion, but only with the tendency to do it. If the inertia is so great that it can't be moved, or with the force applied it won't move, then of course there's two options: either A, leave it where it is, or B, apply a bigger force. And I guess think about that with regard to the scrummaging example. We have 8 players in scrum pushing against 8 other people scrummaging against them, and they push in rhythm and timing against that resistance, but that resistance is too forceful. What do? They either have to be more coordinated in terms of their applying that force, or they have to push harder. And if they don't, they're not going to go forward. And if they don't go forwards, the other team might push them back. Okay, so you've got those concepts at play here. I've asked the question here: what is the only feature of a human body that can generate force? Now, there's only one, and obviously we kind of answered it. So the only object in the human body which can generate a movement force is a muscle. Okay, look, I've got here the lateral head of the gastrocnemius, just to emphasize that. This muscle can pull, and of course it's then going to pull on the Achilles tendon, and it's going to pull on its insertion, and of course that's going to cause plantar flexion or toe pointing for us to stand on our toes or to start a jump or whatever it happens to be, to be in the running action. So that muscle is the only thing that can generate force from within the body. Now, the other thing that we need to just notice about muscles is that they can only pull. Okay, there is not a muscle in your body which is capable of pushing. Right, I want you to think about that for a second. All muscles can pull. Now, we could go into the physiological structures of that. We could go into sort of the actin myosin and the cross bridges and all that stuff. But more importantly, we just need to recognize that because muscles can only pull, what we tend to find is that they work in pairs. Now, you guys already know the theories of this, so I'm not going to go into any detail about this, but that pairing now should make sense to you. Why do we have a tibialis anterior, gastrocnemius and soleus working as a 3-part pair? Well, it's because the gastrocnemius can only pull on the talus. Sorry, on the calcaneus. Let me get my bones right. It can only pull on the calcaneus. So therefore, that calcaneus has to, or that foot, that ankle needs another pulling force on the opposite side, in this case the tibialis anterior, to pull on the foot to cause that dorsiflexion. Okay, so that's why those muscles work in pairs, and it's really nice to make that connection. Even from the synoptic level, if you're working with A-level students, for example, it's good for them to make that connection. Now, that leads us into some really interesting stuff. We're going to look at initially 2 types of motion, then we're going to summarize with a 3rd type of motion. We want to look at the notion of linear motion and the notion of angular motion. And let me be clear, we're going to do a whole heap more work on each of these. This is just the big picture. So what I'm going to do here, let me actually get my, that's not what I want to do. Let me actually get my toolbar and let's make some kind of circle. Let's make a circle. Make a circle, which is, I don't know, it's kind of a white circle. Let's consider it to be some kind of ball of some kind. Okay, so whatever ball you want that to be. So what have we got here? We've got a ball. Let's call it a tennis ball. Let's call it a table tennis ball. Let's call it a shot. Let's call it a golf ball, whatever. So the key thing I want you guys to realize is that it's possible for this ball to move in 2 ways. Okay, so the first way is like this. When a body, the ball, moves in a straight line or a curve, I'm going to come back to the concept of a curve in a minute, with all parts moving at the same time, same velocity, and same direction. And that, of course, is what we call linear motion. Now, how would we achieve that? How would we cause this object to move in a straight line? Well, the first thing we need to do is we need to identify where its center of mass is. And I've just hand drawn it there. You could be very specific and measure the center of mass. This object is what we'd call a uniform object. Okay, so all of its mass is distributed equally in all directions. So therefore, its center of mass is in the middle. Please be reminded that not all objects have their center of mass in the middle, including you, including I. Okay, so on that basis, if we want this object to travel in a straight line, let's say we want it to travel in a straight line to here, for argument's sake, we want it to travel to there. What we'd have to do is why did I close my toolbar? We'd have to take the toolbar, we'd have to take our force and we'd apply that force through the center of mass. That was meant to be directly through the center of mass, by the way. And effectively, by moving the force through that center of mass, this is force, let me be clear, by applying that force through the center of mass of the object is going to move in a straight line. Now, very important, we refer to this as a direct force, Okay, so a direct force. A direct force goes through the center of mass, the center of mass. And if you're thinking, I'm not sure about that center of mass concept, we're going to do that in just a few moments. So just be comfortable with not being sure about it for the time being. So a direct force goes through the center of mass and it creates linear motion. Okay, now, linear motion. Let me now address the idea of the curve. You might be thinking, well, why would you get a curve then? Well, let's imagine we've got a slightly different environment. Let's imagine we've got our ball here, and let's imagine that it's a shot, as in a shot put. Well, of course, what's going to happen is that the ball is going to have a force applied through its center of mass like this, but of course, what's going to happen is that the force of gravity is going to act on it, and it's going to come to rest, somewhere over here. So we get an arc. But the point we would make is when we have got linear motion, we get what we'd call a curve. And we could refer to it as a parabola. And what that means effectively is that it's symmetrical. Okay, because there's standardized forces acting on this shot as it travels. Okay, so rather than it just traveling in a straight line and keeping going forever, of course, our Newtonian physics doesn't work that way, and it is brought back down to Earth with the combination of its mass and gravity, its weight force. So therefore, we get a parabola. Okay, but it's still acting with linear motion. It's just that while it's in motion, there's another external force. It's the weight force acting on it. Now, something different happens if we take the same object. Let's make our circle again. We make our circle again somewhere over here. I haven't quite made it exactly the same, but you get the idea. So we've got our circle again, and let's again put in here that we've got our center of mass. So there's our center of mass, approximately in the middle of the ball. If we were doing this with ruler and protractor, we'd get exactly in the middle of the ball. Excuse me, I'm struggling with that. And what we're saying here for angular motion, it's when a body or part of a body moves in a circle or part circle. So I want you to imagine this time that on this occasion, the force is applied here. Okay, the force is applied there. All right, so we've got force. Let's call this one. Let's call this one over here. This was F1. Let's call this one F2. Well, now F2, of course, it's been applied away from the centre of mass. So what I'm going to ask you to do is use your intuition and think, what is that ball going to do? Okay, probably it's going to go somewhere in that direction, right? You know, you think if you had top spin a tennis ball or table tennis ball, something like that, it's probably still going to move in that direction because the force ultimately is going in that direction. But what it's also going to do is that it's going to spin, okay? It's going to spin, and spinning is a classic example of angular motion. Why? Because the body is moving in a circle. It's moving in a circle. So can I just reinforce the importance that when bodies move in a straight line or a curve, they're moving with linear motion. And by the way, the examples of pure linear motion are extremely rare. And when a body moves in a circle or part circle, that it's moving with angular motion. You might want to say, well, why a part circle? Well, imagine that it's probably a bad example, this one, but if the ball's spinning and before it has time to complete its full first circle, it meets an external force. Well, then, of course, it's not going to spin anymore. Okay, so therefore, a part circle is still indicative of angular motion. Now then, let's move this on. In fact, folks, I'm right on the verge of having a real coughing episode, so I'm just going to pause just 1 second. Thanks for being patient with me, folks. Hopefully there won't be too many more incidents of that. So look, let's have a look at WS 3.1, Force of Motion 1, and we'll go into number 2 as well. Complete the worksheet to learn about linear and eccentric force. Actually, that reminds me, goodness, can't believe I didn't tell you that. So I should have said over here, let me just go through the same process. Over here, if we've got a force off the centre of mass, we call that an eccentric force. Now, don't get that confused with an eccentric contraction. An eccentric force. Secondly, that eccentric force is away from centre of mass. Crikey, I've missed out kind of a central part of this. And it produces angular motion. Okay, so that is by definition how we produce angular motion. Now, the only thing I'm going to say here is that sometimes we use the concept of centre of mass here for objects that we're talking about in this context. When we later look at levers and we look at particularly principle of moments, we're going to look that it's a force applied effectively away from the fulcrum, okay, or the axis of rotation. And on that basis, we can think that an eccentric force is also what you might refer to as a torque, a torque, a torque. And a torque is effectively a force multiplied by its distance from the fulcrum, in this case the centre of mass. Okay, so that's what we mean by that. By the way, a torque is also called, it's an odd name, this confused me a lot when I first heard it. It's also called a moment. So an eccentric force is also referred to as a torque or a moment. Just be aware of that for later to do. It doesn't really matter for now. Let's move it on. We are going to talk about general motion in a moment. But 3.1 here, force of motion. On the diagram, draw arrows to represent the linear and angular forces acting as Usain Bolt leaves the blocks. So we're looking at Bolt here as in his kind of acceleration phase. What is it about him that moves with all parts of that part of the body moving in a straight line or a curve. And we've only got a couple of parts. Let me put my toolbar back on again. We've only got a couple of features really. So let's take a white line. We've got here his head and his torso move in a straight line. Okay, so his head and his torso move in a straight line. Okay, so we can imagine if we were watching him sprinting front on, his torso would move down the track, and broadly speaking, it's going to move at the same time with all parts moving in the same direction at the same speed. His head, likewise, okay, yes, it moves up and down slightly, but broadly speaking, it's moving in that way. But what we need to do is what features of this body are moving with angular motion in a circle or part circle. And this, in my opinion, is where it starts to get really interesting. Let me choose what should we go for? Let's choose a sort of a minty green. So for example, his hip is moving in a circle or a part circle. His knee is moving in a circle or a part circle. It's effectively going through flexion and extension, both at the hip and the knee. His ankle is moving in a circle or a part circle as it goes from a position of plantar flexion to dorsiflexion as he pushes off. We could look at the back leg as well. We've also got the shoulder, which is moving in a circle, part circle, but by the way, in both directions, depending on the phase. We've got the elbow. Now, the elbow in sprinting broadly remains constant. The angle doesn't change a great deal depending on the action. But we've got these ideas of angular motion. So how could we summarize the entire performance? Well, we'd summarize the entire performance to say that we've got just off the page there. Over here, we've got linear motion plus angular motion equals, and we've got a concept called general motion. General motion. So where we've got a body performing both examples of linear and angular motion within the single performance, we call that general motion. And just so you're aware, there probably aren't any examples in reality where we don't get general motion. We tend to always, where it's anything other than general motion. In almost all cases, bodies move with a combination of linear and angular motion, so we tend to find the general. On the diagram below, draw two straight arrows, one which shows the force which would need to be applied to generate linear motion and another to generate angular motion. Okay, and the dot represents the centre of mass. So what we're going to do, let's go for our line. Let's do our direct force first. Let's do that in black. There's our direct force. Okay, let's label that. It's just about through the centre of motion. That's our direct force, and that direct force is going to lead to linear motion, straight line or curve. And let's use a red line, and let's imagine that we are applying a force here, that red line, and that red line, of course, is what we call the eccentric force. And that eccentric force is going to produce angular motion. Okay, angular motion. All right, so obviously we're not saying we'd apply them at the same time, but the point is we can apply different types of forces to the ball to get different types of actions out of it. Okay, worksheet 2 over here. We've got complete the worksheet to learn about linear and eccentric force. Answer the questions below to decide whether the motion is angular or linear. So we've got the luge here. So let's use some ticks. Does the luge rotate around an axis? Well, we're going to say no, it doesn't. Does the luge move in a straight line? Yes, it does. Does the luge move in an arc? Well, it depends which part of the track it's in, but no. Now, therefore, we can make a pretty good argument that this is linear motion. Okay, linear motion. All right, now, I know someone's going to say to me, well, they steer by moving their feet and twitching their ankles and doing eversion and inversion. Yes, that absolutely would be examples of angular motion. The boxer's fist, just the fist. Does the fist rotate around an axis during this performance? No. Does the fist move in a straight line? Yes. Does the fist move in an arc? No. No. And therefore, what have we got there? We've got another example of linear motion. This one, by the way, this image is wrong. This should be of a tuck somersault. If you look in your resource pack, and in fact, probably in your notes, you've probably got a tuck somersault. Does the body move around an axis? Yes, and in fact, we call it the transverse axis of the hip. Does the body move in a straight line? No. Does the body move in an arc? Yes, and therefore, we've got here angular motion for that rotating body, for that circle, part circle. So linear motion plus angular motion equals, and of course we know that that's general motion. And can you think of any sporting examples which are purely linear? And I urge you to get your students to rack their brains about this, because there broadly aren't any. The best ones you're going to come up with are things like luge, skeleton. You might even get someone who says the flight of a shot put. Okay, the flight of a shot, but of course it depends. That would insinuate that the shot is not rotating around its axis at all. If you ever watch the flight of a shot put or of a shot very, very carefully, it does tend to rotate. So it's theoretically possible for it to be a linear motion, but to get the force moving so directly through that center of mass is pretty unlikely. Okay, it's pretty unlikely. So I'm going to quickly change the canvas and we're going to move on to center of mass. Okay, we're moving along nicely. Let's move this forward. So just as a very quick sort of activity, and I would encourage you to think about the students doing this before they do the learning we've just talked about, is you've got this activity here, A3.1 over here, force of motion. So the way this works is, and I find it works best with straws. You can try it with pencils, but you might, in my opinion, straws are the best way to go here. Effectively, what you're trying to get the student to do is you're setting up a little test where they're going to get something light, such as a pencil at this end of the desk, and they've got to apply a force to it so that it moves as linearly as possible down the desk, and ideally off the end of the desk. So it's like that, we've all played that thing with the penny where you're trying to get it to hang over the end of the desk. It's a bit like that, apart from you're not trying to get it to stop at a particular point, you're trying to get it to roll all the way off in a straight line. And of course, what's going to happen in reality is when they get their their straw's going to be whatever, it's going to be like this, isn't it? They're going to have their straw like this, and of course they're going to apply a force in this direction, and even though they think they're in the center of mass, in reality this thing's going to move in a circle to some degree. Okay, so it's a really challenging thing to do. So the intuition of that is that they're very specifically seeking the center of mass of the object. I mean, again, you just want to start asking questions. They're assuming the object is at uniform mass. Is it? I mean, it might not be. And a couple of other bits and bobs as well I would get you to think about is that we've got a little section down here where it says to them, right, now modify your straw or modify your pencil. So effectively you've got blue tack to do it. What you find students do is that they'll have their straw over here, and what they're going to do is often they'll make a hole in the straw and they'll get their blue tack and they'll put their blue tack as a big ball in the middle. Okay, they'll do it like that, so they can literally see the center of mass. But do they do it in the middle? Is it balanced? Is it balanced on both sides? Then you get another group who will do the following. They'll try and just make it roll better, and you'll find that a lot of students will put blue tack around here, and we'll put blue tack around here, and then they'll still apply a force through the center of mass. And what this is doing, this is giving more stability to the object, because effectively what it's doing is it's increasing the object's mass. It gives it more stability. So therefore, and it allows it to roll, I guess, as well. But the chances of them getting these surfaces all perfectly smooth are really limited. So what you're going to find is it's a real trial and error thing, and it's a beautiful activity, not because it's complex or clever, but because they can't stop thinking about, they sort of become obsessive about finding that center of mass point, and therefore applying a direct rather than eccentric force. And you've got the element of competition if you want them to sort of score points and what have you as well. Let's move on. Center of mass. I see different definitions for this all over the place, so I put in 3. Just cherry pick the one you want to use. The point of the body where most mass is distributed is what we mean by the center of mass. So if we think about our uniform objects, the golf ball, mass is distributed evenly in all directions, so therefore the center of mass is in the middle. But not all objects are shaped that way. Okay, so we think about the human body. The human body has a lot of mass in its middle and a lot of mass around its head, so we tend to have the center of mass kind of in the navel position, and it can also move, because if the arm gets raised to here, the center of mass will go up because the mass is then distributed in a slightly different place. Okay, so we can manipulate that center of mass. The point of the body where mass is distributed evenly in all directions. Now that's only possible in uniform objects. The point in the body representing the mean position of the matter. So if we look at a human body, for example, or a boat, or a shot, where is its mean position in terms of its matter? Now for a human being, that mean position is in the navel kind of region. That's on average, that's where if you apply force, you're going to get that linear motion concept. A direct force it would be, of course. But the point I would make to you is that center of mass is conceptual. There's not an actual thing in there. There's not an actual point. It can change. It's an idea. It's a concept. Okay, so on that basis, go back to the straw experiment. Conceptually, there's a centre of mass somewhere in the middle of the straw. But that's assuming that the straw has been built perfectly, and it might not have been. You can't find the centre of mass by touching and looking at it. It's there as an idea. And the other thing I'd say about centre of mass is the centre of mass can be out of the body. And I'll come back to that point in a few moments' time, but it emphasises the notion that it's conceptual. So look, what have we got here? We've got a couple of worksheets. I'm not going to spend a lot of time on them because they're fairly obvious. Mark with a dot the centre of mass of these symmetrical objects. The first has been done for you. So this one's going to be somewhere in here. This one's going to be somewhere in here. This one's going to be somewhere in here. You might literally be drawing a sort of a straight line to find that point. This one's going to be somewhere in here because you're drawing that line to find the point. This one's going to be in here because because it's uniform. This one is going to be somewhere in here, and you get the idea. Those uniform objects is fairly easy. Now, this is where it gets a little bit harder because you've got the same activity now with asymmetrical bodies. So I'm just going to take a couple of examples. Let's imagine, let me choose a colour we're going to be able to see. So let's imagine that this person has got her head below the bar, she's got her legs below the bar. Okay, so there's a lot of her mass which is below the level of the bar. Let's imagine that the centre of mass is actually here, outside the body. Okay, maybe on the bar, or if she'd arced enough, under the bar. The centre of mass of this performer could be back here somewhere, again, outside of the body if she's arced enough. This athlete here is lower down, she's in a tuck position, and she's got a surfboard attached to her feet. So therefore her centre of mass is going to be lower in that situation. Again, this athlete's got an arm behind her, an arm up, her head is back, this leg is forward. So again, where do we put the centre of mass of this object? Well, we're saying the majority of the mass has gone in that direction. So what we're going to say is that the centre of mass is somewhere like there. Again, here, possibly, there might be outside of the body. This one here, centre of mass, it's sort of a normal sort of body shape, but she's got a javelin in her hand. So therefore the centre of mass moves up a little bit to be a little bit above the navel. I'm jumping around, but this one here, we've got a boat, a sail, and two people. So it's not going to be in the navel. The centre of mass is going to be here, and we kind of know that one because the centre of mass is above the base of support where the boat is touching the water. And with this one, we've got 1, 2, 3 athletes all kind of connected to each other. The centre of mass of that, when we change colour, is going to be somewhere in the middle of those three. Okay, so it really encourages students to start thinking, well, what is centre of mass? How do I know where it is? And if the athlete, for example, raises their arm, or both their arms, here's a good example, or raises their knee, it also raises their centre of mass. Why? Because it's the point in the body representing the mean position of the matter, what we're made up of. Let's move on. A little experiment to try it. How does this work? What we're going to encourage you to do is a little practical. So here we go. We go here. To understand centre of mass, you need to grasp the concept of the centre of centre of mass will be towards the heavier part of the shape. In a regular symmetrical shape, it is simple to work out where this is. Just find where the lines of symmetry intersect, and voila. 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 For 3D regular shapes, it is the same. You need to find the centermost point of the object. For irregular shapes, like people, it is more complex, but the intuition comes from thinking about the distribution of the object's weight times mass times gravity. Another way of thinking about it is to ask the question, which point represents the most average weight of the object? How to work out the center of mass of asymmetrical bodies. So what we're going to do is we're going to take these shapes. Let's take this one, for example, just for argument. So we're going to take these shapes over here, and we're going to cut them out. Okay, so it says here, cut them out. So you're going to cut this out. You're then going to take this paper shape and you're going to glue it to a piece of card and then cut out the card. Folks, I'm so sorry. Struggling with a cold here. How embarrassing. So you take the shape, you put it onto a piece of card, you then cut the card out. And then what you can do is you can bring this now card shape, you can bring it to here, and what we want the student to do is we want the student to sort of push the shape off the edge of the table. And they keep pushing it and pushing it and pushing it until it gets to the point where the paper is just about to fall off the table. Now, wherever that line of the table is, we draw a line like that. So it might be that it's across there, for example. We then turn the shape around 90 degrees. And this time we push the shape towards the end of the table. And this time we might get to this point here. And what that means is that the center of mass is in that point there. Okay, and you can try that with these different shapes, and the students can push them towards the edge of the table just to the point of tipping, and at the point of tipping they draw their line, they turn it 90 degrees, repeat, they find their center of mass. Okay, so that I'll keep going, folks, okay, bear with me, apologies. It's a really beautiful little practical experimental feature for intuition. Okay, so again, could this be a first access resource, first access for center of mass? Could you get the student thinking about center of mass before they know even what it's called? And could you get them thinking about it in this way? Let's move it down. A couple of points about center of mass and stability. We want to know when is an object stable and when is it, let's call it unstable or instability. I perhaps could have put, so it's not just about stability. Sometimes in sport we want instability because we're accelerating, for example. So let's take height. So with height, what we're saying that taller objects, or bodies I probably should put, taller objects are less stable. Okay, so I want you to give an application of that. Think about your own. I'm going to say that a rugby player gets low to tackle. Okay, gets low to tackle. Now, why would they do that? Well, they're lowering the height of their center of mass, and as a result of that, they are increasing their stability. In other words, more likely to make a successful tackle. Now then, we've got the mass. So the more mass, up arrow, more mass, the up arrow, more stable. Okay, so if an object has more mass, it tends to be more stable. So on that basis, what do we tend to find? Let's keep with the rugby example. What do we tend to find as a prop forward in rugby? We tend to find a heavy, large mass player, and they also happen very often not to be that tall. Apply that to the height concept. So more mass, the more stable. So I want to keep with the rugby, but a different example. By the way, I don't play rugby. It's not my sport, but I'm just happy to be using examples here. So what we could say here, so we could say the greater the pack weight, the more stable the scrum. Okay, or the maul or the ruck or whatever. Okay, so let's have a look at base. And when we talk about base, we're talking about base of support. Okay, base of support. What we're saying here is that if the base of support, so if we've got an increased base, then we've got increased stability. So I want you to think, for example, in the handstand, headstand position, if we were to look at the points of contact on the base of a handstand, so this is a handstand, the handstand might have something like hand position, and there's our base. Okay, so there's our base. Whereas if we take a headstand position, we've got head position, hand position, and there is our base. It's a much bigger base of support. So what do we therefore find? That the headstand, if done with equivalent quality, the headstand is more stable as a result of that. And again, think about if we don't want to be knocked back, or we don't want to get knocked over in combat or in impact sports, for example, we make a large base, so we're less likely to be unstable. And finally, we've got what we call line of gravity. Excuse me, folks, line of gravity. And this is the idea that line of gravity, first of all, a little point. The line of gravity is always from center of mass. Okay, so that's important. And the line of gravity is always to the center of the earth. Okay, so we've got the line of gravity is always from the center of mass and always to the center of the earth. Okay, so what would that mean? Let's take let's go back to our example here. Let's go back to our example up here. Look, we've got the center of mass of this object is here, and it's above the base. Okay, it's above the contact between the boat and the water. If the center of mass was to sort of be outside that base, think about someone like, I'm going to probably draw this really badly. Think about someone like a skier whose skis are in that position, okay, so they're skiing down a mountain, but their center of mass is outside of their ski position, they're more likely to slip and to slide as a result of their center of mass not being above, or their line of gravity not being above their base of support. So line of gravity should be above base of support if we want stability. But can we clarify that sometimes we want instability? Line of gravity should be outside base of support if we want to accelerate or decelerate. It's not always stability that we want. Okay, nice. We've got 3 little questions. I'm just going to take a very brief break just to sip some water. I'm also going to check the time, see if we've got time to squeeze these in, and I'll be straight back. 1 sec. Okay, so look, we're actually going to leave the questions for the start of next session. I mean, we could look at those, but we're not going to have any time to sort of summarise and to answer any questions that you guys might have. If you have questions, please post them into the chat box there, or you can post them to us on Twitter. Your call, okay? So it's get us some questions on there, and we'll answer those. What I want to address though is there's a question there on the canvas, which I think is kind of a really nice thing to summarise, almost to have as a closing thing for us this evening, and that is, one of the things I like about centre of mass is this concept of being able to manipulate it, being able to raise the arm and the centre of mass coming up, being able to go into the crouch position, the centre of mass lowering down, and therefore becoming more stable because the mass is closer to the ground, and so on and so on. But one of the other things I really like is when a centre of mass becomes, or when we look at centre of mass in relation to a projectile. So let's think about a long jumper, for example. A long jumper, we know that their centre of mass is going to be sort of in their navel position because they're a human being. On an average, that's where that is. But the interesting thing is that once they sort of push off the board, and the moment that their toe leaves the ground, the flight path of that centre of mass from the navel, or slightly up because they've raised their arms and they've brought their knee up and they've even tilted their head often, so they've brought that centre of mass up. But as soon as that toe leaves the ground, the flight path of the centre of mass is completely predetermined. So what we mean by that is that the flight of the centre of mass will be completely like an arc and completely parabolic, no matter what the athlete does. And this is a law called the conservation of momentum. And effectively what that means for the performer is that at the moment of takeoff, if they're able to raise their centre of mass as high as possible without losing kind of that force application to the board, that what they're capable of doing is raising their centre of mass. Imagine centre of mass being at this height and another centre of mass being at this height because they've really stretched higher, and then they both move in a predetermined way. Well, the one where the centre of mass is higher is actually going to land a further horizontal distance away from the takeoff. And that is why, for example, you see athletes manipulating their centre of mass by raising their arms, by tilting their head, by lifting their knee, by doing that. So that conservation of momentum principle is very important. Now, that only applies to a human being because a human being is heavy. If we were looking at a very light object, this conservation of momentum doesn't happen because A, it might move very fast and have lots of air resistance, things like a shuttlecock, or for example, it's because it's not heavy enough, the air resistance might sort of become the dominant force rather than the weight force. But if it's a heavy object, that centre of mass will fly with that principle of conservation of momentum, a predetermined flight path. And I personally think that's a fascinating application of these sorts of principles. Okay, so look, we're gonna just check for questions. We haven't got too much coming in at the moment, so we'll kind of we'll assume you guys are not sort of chomping at the bit to ask us too much. I want to address something that I think it was Ali. I think I asked before. I saw it come up in the chat. Alice Haberfield. Apologies for misnaming you there. Alice asked what a torque was. A torque very often confuses students. So very predictably, if we're not accustomed to it, it's probably confusing for us as well. So a torque is simply a force. The only difference between a force and a torque is that the torque is applied away from the fulcrum. Okay, so in a ball, I don't have a ball near me that I can quickly show you, but if we apply, or have we, Marta? No, I don't think. What have you got? What are you going to come up with? If we apply a force direct to the centre of mass, that's a direct force, then of course we're applying a force, that direct force we looked at, and it will produce linear motion. That ball will, accelerate up that way. If we apply a force away from the fulcrum, in this case the centre of mass, then that ball is going to start to spin. In this case, sort of top spin. More typically in golf, we'd hit a backspin shot actually. And the torque is a product, so a multiplication of the force applied by the distance away from that fulcrum or the center of mass. So that is the only difference between a torque and a force. A force is applied through the center of mass. A torque is applied away from the center of mass, an eccentric force, and therefore we can multiply the force itself by the distance from the center of mass or the fulcrum, and we can get the reading of torques. The only thing I say in addition about torques is that torques are sometimes also referred to as moments. I've never really understood why, but a moment and a torque are synonymous. They are effectively the same thing. Okay, so if you see a moment, and we're going to look at the principle of moments later in the course, a moment and a torque are synonymous. So again, you know, if I just go onto the side view here, my bicep, not that it's particularly impressive, let me try not to be too crackly, my bicep is applying a force to my radius here, and my radius is some distance away from the pivot, from the fulcrum, from my elbow. So however much force I apply, I can multiply by the distance of the application of that force, and I can measure the torque in Newton meters. So that's what that is, and it's a really beautiful concept. You probably hear about torques more to do with cars, and that's because, of course, the car wheel is turning, the force is being applied to produce angular motion. And what was that, Marta? Oh, of course, a screwdriver now as well. Yeah, of course, because again, we're applying a force away from that center of mass. So we apply it in that kind of principle. So anyway, yeah, I wasn't really expecting to get my bicep out in the show tonight. I don't think anybody really would have asked for that. Just a couple of last things before we sign off. Before we had our sort of mess up at the start when we had went badly wrong with one of our microphones. We just had a little recording before the show started, and that recording was about the session. We've actually got 2 sessions next week. We've got the biomechanics session, which continues on the Tuesday as normal for the 6 weeks. But we're also doing a free CPD session on the Monday, and this one's on increasing student activity. Now, I don't know if I can ask for your attendance and time for 2 consecutive evenings. The CPD one is at 4:30 on Monday, the 2nd of October. The link is in the description to this live show now. So have a little look at that. If you're interested, come along. It'll also be available. We're going to look at increasing student activity. So it's going to be like group activities, questioning techniques, how we might apply an exam question, these sort of things. And it won't just apply to biomechanics, it'll apply more broadly. If it's of interest to you, then by all means jump on that and get involved. We actually have an 11-month CPD course, and that is actually part 3 of that CPD, and we're just broadening out because a lot of people have been asking us to take it. So if you're interested, jump on it and come and get involved. And I have a big request of you. I meant to ask this right at the start, I completely forgot. If you could do us a favour, it really helps us. If you would be willing to, and I ask very graciously, you don't have to, of course. If you could subscribe to the channel and you could like the video, that really helps us, because it means that our other videos, for example, just become a little more prominent in listings and that kind of thing, and it's really nice for us. So if you're able to subscribe, you'll also get notifications of when we release something new, and a like would be very much appreciated. Equally, if you thought it was rubbish, dislike it. We listen to the feedback also. So yeah, we'll go from there. So look, unless I'm missing something, I've got something through on Twitter, so let me just check what it is. It might not be for this. It's not. Unless we've got any questions pending, I'm going to sign off. Marta, anything you wanted to ask, or anything you think that would be worth clarifying? No, you're happy. You're going to go back now to thinking about Spain and Catalonia for the rest of the evening now, I'd imagine. No. So look, to everybody who's attended this evening, we massively appreciate your attendance. We try really hard with these things. We had a bit of a cock up with the audio right at the start, before the session, I should add. But that's because we're real, and so sometimes these things happen. You learn from these things. Well, I still don't know what happened, but yeah, we appreciate you being here. Marta, if you could sort of sign us out. We wish you a lovely evening. I think the Champions League's on. Have something cold, have something enjoyable. All the best. Take care.